Hey, all you pre-calc savages, Mr. Murray here, and ready to talk about some new material here. Something I think is totally new. It's called Parametric Equations, and it's pretty cool. It's two equations relating to the same graph. Up till now, you've basically graphed an equation and it had two variables, and now we're using three variables in two equations to draw one graph. And we're going to do a couple word problems in the next couple days where you'll see this applied. But one case is, think about when a punter kicks a football. There's time that's ticking off the clock as the ball is not only going up, but it's also going forward. So you've got a few variables going on. You've got time, you've got height, you've got horizontal distance. So, I mean, this is where you start to get into some more real world things. All right, so take a look at this. T, they use T because it usually stands for time in the application kinds of problems, but T is what's called the parameter, the common variable that ties these two together. So we're going to graph this set of parametric equations over this interval for -3 to 2 for T. So the table's already been set up for you. And so let's plug this in. Now x, meaning the x coordinate will always be t squared minus 6. So that will be -3 squared is 9. 9 minus 6 is 3. Plug in -2. I'm going to do all the x's first. Plug in -2, you get 4 minus 6, -2. Plug in -1, 1 minus 6, -5. Plug in 0, -6. Plug in 1, -5, 2, -2. For our y coordinates, y is defined as always being -t divided by 2. So when t is -3, y is going to be -3 over 2, or +3 halves, or 1.5 if you prefer. -2 will be +2 over 2, which is +1. -1 will be +1 half, or 0.5. 0 will give you 0. 1 will give you -1 half. And 2 will give you -2 divided by 2 is -1. Plot these points, and you only plot it's on the xy plane, so you're plotting the x and y values. These are the coordinates as dictated by time. So 3, 3 halves. So 3, 1.5, -2, 1, -5, 1 half, -6, 0, -5, -1 half, and -2, -1. And that's the end because we were only graphing over this very specific interval for t. So connecting the graph, it's not enough to just connect the dots. One thing with parametric equations, since there's usually this hidden time component, and the way to represent that on this graph, because all this shows are the x and y coordinates, is to use little arrows to indicate the orientation of the curve, like which direction we're moving in. And we started here and we plotted as time went on, and it went in this direction. So usually people will do that, just add a couple arrows right on the curve, and that shows the direction or the movement of whatever these equations might represent. Okay, and now we're going to change this to rectangular form by eliminating the parameter. Rectangular form is what you've always used, just y and x. So you've got these two equations, x equals t squared minus 6, and y equals -t over 2. You're just going to use some algebra, and every problem is a little bit different, but you basically one way to do this is solve for t in one of these equations and substitute into the other. So this one would be pretty easy to solve for t in. If you multiply both sides by -2, t is equal to -2y, and now I'm going to go to this equation and replace t with negative 2y. So x equals negative 2y squared minus 6, and I'll do a little simplifying there, and we get x equals 4y squared minus 6. And that should come as no surprise to you, because what you're looking at here, I mean, you may have guessed, maybe only a portion, you weren't 100% sure, but what you're looking at here is a sideways parabola, which is the y squared and x to the first power, and the vertex being at negative 6, 0. Negative 6 is the x-coordinate, 0 is the y. So changing it to rectangular form can help give you a little confidence in your graph if you have a pretty strong recognition of equations and what kind of graphs they make. However, you still really need to do this, because this shows you the direction that you went in. If you only change it here and then just drew this graph, you might not know, well, which way was the curve moving in. So that's that. I'd also like to just take a moment and show you that you can do these on the graphing calculator. You have to change your mode. It's normally on function mode, which is y equals, where y is isolated, to parametric form. That's polar form, which we'll be doing later, and sequence form. But for parametric form, if you now go to y equals, where we input equations, the inventory here, you'll notice it's all been switched around to x1 equals and y1 equals. There's two equations for each graph, and they're in terms of t. And when you go to hit this button to input where you normally put x, it's going to use t. So I put these in here, and I'm going to change my window just because I want to see my t. You have to sometimes define that, and so sometimes you have to put a little thought into these, but you got to change that from negative 3 to 2. And if I hit graph, you kind of see it. There it is, just the portion of that. And when you turn the trace on, it's kind of cool, because at any given spot here, you can see the time and basically the x and y position at that given time. So it's kind of showing you all three at once, which is kind of cool. And so you can see it in that flow in that direction. As you increase t, it moves in this direction. Okay, let's try one more here. This one, a classic. Got some trig here. Everybody loves trig. So here's what we got. X is 2 cosine of theta. Y is 4 sine of theta. I'm going to make a table. Sometimes when it's trig, instead of using t, they'll use theta. That's the parameter, or the common variable that's tying those together. And you can use any theta values you want. It didn't specify any particular range. So I'm going to recommend maybe we'll stick with the quadrantal ones. Those are good round numbers to plug in. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. If we need to plug in more in between to get a better idea of what's happening, we always can. We can always go back. So I'll do all the x's first. Now this is going to give you a little warm-up, getting back in touch with your unit circle here. But plugging 0 into here, 2 cosine of 0. Cosine of 0 is 1. 1 times 2, 2. Plug pi over 2 in. Cosine of pi over 2 gives you 0, 0. Plug in pi. Cosine of pi is negative 1, so we get negative 2. 3 pi over 2, we get 0 again. And 2 pi, we get back to being 1, so we get back to being 2 there. Our y values, plug these into 4 sine of theta. 4 sine of 0, that's 0. 4 sine of pi over 2, sine of pi over 2 is 1, so we get 4. Plug in pi, we get 0. Plug in 3 pi over 2, we get negative 1, so negative 4. And 2 pi, again, we get back to 0. And plot these points in this order so you can follow the direction that the curve moved in. So we got 2, 0 as our first point, 0, 4 as our next one, negative 2, 0, 0, -4, and 2, 0. Hey, back to where we started, and guess what shape we got? There's our old friend, the ellipse. I told you conic sections were going to be coming back in here, and put those directional arrows on there to indicate that. And notice I didn't say it in the directions because it does not need to be said for parametric graphs. Include the arrows. And now we're going to change this to rectangular form by eliminating the parameter. So I'm trying to write this just in terms of x and y. I'm not going to take the same approach I did in the last one and try to isolate theta, because then you'll be getting into taking the inverse sine or the arc cosine or something like that. And I can do a little bit better than that. One thing is this. If I isolate each one of these, if I just isolate the trig expression, so if I get x over 2 equals cosine of theta, and y equals 4 sine of theta, so y over 4 equals sine of theta. Instead of going that one extra step and isolating and solving for theta and then trying to plug it into the other one, I'm just going to stop and think, how do I know sine and cosine are always related? Ooh, I'm going to go back to a trig classic, which is sine squared plus cosine squared is equal to 1. The Pythagorean identity, the most classic version of it. And now I'm just going to take out what is sine of theta equal to. Sine of theta is y over 4. So remember, sine squared means I'm squaring that whole value of sine, and cosine is x over 2. So I'm squaring that whole thing, and then you have this, y squared over 16 plus x squared over 4 equals 1. Or some people like to have the x quantity first, so it doesn't really matter to me. Just like sine squared plus cosine squared is just as good if cosine squared comes first. But notice the equation. It's an ellipse because it's x squared and y squared. They're being added. The bigger number is under the y quantity, so that is a vertically stretched ellipse in the y direction. And that 16, the square root is 4, and that is your kind of vertical radius, half of the major axis. Square root of 4 is 2. That's your horizontal radius, or half of the minor axis. So it all kind of comes together here. Pretty cool. I'm going to end this video right here, and I'll make a part 2 for the back half of the worksheet, because you still got some good tricks to come here. So hang on to your hats, kids.